Okay, so good morning to everyone. First of all, let me thank the chair for the introduction, and I would like to thank the organizers of the conference. I'm very glad to be here today, and especially in the WISE section. So today I'm talking about fiber Bragg gratings for pulse wave monitoring. So let's start with fiber optic sensors in general. They are very widespread for a lot of applications, from structural monitoring to biomedicine, and their market is growing year by year. It is projected to grow up to $8.2 billion by 2032. But among all the fiber optic sensors, fiber Bragg gratings, FBGs, are becoming a popular solution, especially for the measurements of temperature and strain, but not only, because of their advantages, features, like the wavelength encoded nature of the output, for example, but also the relative low cost, the longer lifetime with respect to other sensors, the great flexibility of design, and many others. As we know, an FBG is a periodic perturbation of the refractive index in the core of the optical fiber along the propagation direction, and it works like a band rejection filter, because when a broadband spectrum passes through the grating, it reflects a narrow band centered around the so-called Bragg wavelength, which is equal to 2 times the effective refractive index of the core mode multiplied by the grating period. And but why using FBGs? The key point is that we can use them as a sensor because they work like sensors, since when the environmental conditions around the FBG change, mainly temperature and strain, also NF and the grating period change. And thus, the reflected peak shifts, and the shift is denoted by delta lambda b, and so by detecting the delta lambda b, we can have information about the parameters, the environmental parameters that are changing. This delta lambda b is given by the sum of 2 contributions, temperature and the strain effect. And here we can see the typical values of the sensitivity, temperature and strain sensitivities for a bare FBG, which are 10 picometers per Celsius degrees and 1.2 picometers per microstrain, respectively. So beyond the features that we saw before, FBGs show also biocompatibility, chemical inertness, their immunity to electromagnetic interferences, small size and lightweight, and so we can understand why they can be so attractive in the biomedical field for many applications. For several years, we have been conducting studies on the use of FBGs for monitoring thermal ablation of tumors, different techniques of thermal ablation. And more recently, we are focusing on physiological monitoring. So the use of FBGs for monitoring physiological parameters, but they are used in many other biomedical fields. And in this slide, we can see some examples of the works reported in literature for monitoring by using FBGs, for monitoring different parameters, physiological parameters like breathing or sleeping, body motion, heart rate, and many others. What is the common point? Beyond the use of FBGs, of course, the common point is that FBGs are integrated in some device or structure, like some mattress, the nasal clip, or wearables. But today, the physiological parameter that we will consider is pulse wave. Pulse wave is a mechanical wave starting from the ventricles and spreading through the cardiovascular system due to the rhythmic contraction of the heart. And so the pulse wave propagates through the arteries, and it translates to a dynamic mechanical deformation of the wall of the arteries. It depends, of course, on the elasticity of the arteries, but also on the resistance of the peripheral vascular system. And this is the typical theoretical waveform of the pulse signal. Here we can distinguish two main peaks. The first one is the systolic peak corresponding to the contraction of the ventricles, and then a diastolic peak corresponding to the relaxation of the ventricles and their filling with the blood volume. And between these two peaks, we can see the dichrotic notch, which is consequence. It's a slight pressure rebound due to the closure of the aorta. But why to monitor the pulse wave? It is important because pulse waveform contains information about several parameters, about the cardiovascular status of a subject. So about systole, diastole, but also cardiovascular age, because the pulse waveform depends on some parameters like growth and development, for example. Indeed, if we look at the pulse waveform for newborns, we can see differences with respect to the older pulse waves. For example, it has a lower amplitude and a late systolic peak. And as the body grows, the systolic peak shifts in the early systole, and we can see better the diastolic peak. Other parameters, we saw the age, but also the body part, because if we change the body part where we do the measurement, also the pulse waveform changes. Here we can see from a study present in literature, these results are obtained through photoplethysmography. But if we look at ears or fingers or toes, the pulse waveform changes. And by increasing the age, we can see some differences. Mainly the diastolic peak is very attenuated, and also the dichrotic notch almost disappears. But another study, for example, in the literature, demonstrates the pulse wave monitoring efficacy for detecting the effects of drugs. For example, this study is for assessing the effect of vasodilator drugs, and they could observe the effects of this drug, whereas it was not possible with the standard sphygmomanometry. And of course, a pulse waveform depends on the health conditions of the subject. So, for example, this study focuses on patients affected by peripheral arterial disease. And the authors observed that in the occluded limb, the pulse raise time was late, and so the pulse raise time can be taken as a marker for this kind of disease. And many other factors have an impact on the pulse waveform, like food habits, but also fitness, body height, gender, and so on. So now we have an idea about the importance of pulse wave monitoring. Why can we monitor this physiological signal? But how can we record such waveforms? If we look at the commercial sensors, of course, there are invasive solutions that are based on the arterial catheters. But there are also non-invasive solutions based on applanation tonometry, volume clamp methods, and photoplethysmography. Here, for example, we can see a hybrid solution including a finger photoplethysmography and an inflatable cuff applying a pressure to keep constant the blood volume inside the finger. And so this pressure gives us information about the arterial pressure instantaneously. But in the literature, there are many other solutions. Photoplethysmography in different configurations, which is mainly based on a LED and photodetector to measure the variations of the light absorption and reflection with the blood volume changes. Then we can have also imaging-based techniques like laser speckle contrast imaging. bioimpedance-based techniques to measure the electrical impedance variations due to the blood volume changes, and also displacement-based techniques like the ones which are based on the use of strain gauge. Of course, all these techniques present advantages, but also limitations. For example, photoplethysmography is strongly affected by light, by the light of the environment or the skin tone and texture. Imaging-based techniques can be more complex and expensive. And bioimpedance displacement-based methods typically offer poor spatial resolution and can be also quite intrusive for the patients. So all these considerations lead us to use FBGs for this purpose. And at first, some authors focused on the use of bare FBGs, simply positioned on the body, for example, in correspondence of the neck, the ankle, the brachial artery, and to secure the position of the FBG, they used medical tape. But medical tape is not enough to protect the fragile areas of the fiber optic, and so the grating. To avoid this high risk of breakage, someone else proposed to integrate the FBG in some device like this ring, which has a flexible membrane, and the FBG is glued on the top. But this can be not suitable for all the sizes of the hands. Someone else proposed to insert the FBG, the fiber, in a wristband, so in the silk filaments. And we propose to use FBGs for a simple manufacture technique, with a simple manufacture and a simple operation principle. Basically, we propose to embed the FBG in soft compounds and to include this device, the embedded FBG, in some object easy to apply, like a clamp typically used for electrocardiography measurements. So, going step by step, we basically propose to embed FBG. The embedding can be useful to protect the sensor inside, but also and mainly for sensing purposes, because in this way we can keep the sensor in position and in contact with the structure that we want to monitor, and we can make the FBG sensitive to other parameters different with respect to temperature and strain, like pressure and forces. For the embedding, we can use, of course, 3D printing, and we can use different materials like TPU, ABS, it depends on the characteristics that we want. Also resins if we think about stereolithography. But in our case, we use 3D printing not to print the final device, but the mold to shape the final device, because we aim to obtain a flexible, a soft device. And this final device, embedding the FBG, can be called a patch. So what is the idea for the measurement of pulse wave? The idea is to put the sensor, the patch, on the skin, and in correspondence of a blood vessel. And when the working principle is that when the pulsation occurs, a pressure is applied on the skin surface and so on the lower surface of the patch, and the FBG, which is embedded inside the patch, experiences a strain and it stretches. And so we can see the shift in the Bragg wavelength. And by detecting the shift, we can have an information which is proportional to the pressure, to the arterial pressure, the pulse wave. But before performing the experimental tests, we wanted to perform some numerical simulations in the COMSOL environment Firstly, to quantify the enhancement of pressure sensitivity when we embed the FPG in a patch. So we compare the two configurations. The first one is a bare FPG, and on the skin, on the back of the hand, in correspondence of the ulnar artery, and the second configuration is the FPG embedded inside the patch. And we will use in the experimental test an elastic band to fix the position of the sensor. So we consider these two geometries. A fixed constraint simulates the elastic band, and this pressure corresponds to 120 millimeters of mercury. And the results demonstrated that if we embedded the FPG in the silicon, in the specific silicon that we used for fabricating the patch, the pressure sensitivity improves in terms of elongation and microstrain. And the following simulations are to observe what happens if we change the geometrical features of the patch to select the best features. So we simulated 3 different thicknesses, 1, 2, and 3 millimeters, and 2 different geometries, the rectangular one and the dog bone one. And the results show that if we increase the thickness and decrease the central area, which contains the FPG and is in contact with the blood vessel, we can have a higher pressure sensitivity. So we selected the dog bone patch. And this is the fabrication process, step by step. Also the details of the silicon that we used, the EcoFlex one. So after the curing time, we could extract the patch from the mold and use it. And this is a photo of the final device. So moving to the experimental tests, the first configuration that we implemented is this one. The one that we saw also for the simulation. So the patch is in correspondence of the ulnar artery of the hand, of the left hand. And an elastic band is used to fix the position of the sensor, whereas the second configuration is to integrate the patch inside a clamp used for electrocardiography. In this case, the clamp is positioned on the wrist, and we monitored, in this case, the radial artery. And in both cases, we used a dynamic FPG interrogator to acquire data set at 2 kilohertz for the sampling frequency. So here we can see the results, some of the results that we obtained in the first configuration for 8 healthy volunteers. They are divided by age. The first row shows the results for the volunteers aged from 20 to 40 years, and the second row represents the results obtained for the subject from 50 to 70 years. And the first thing that we can see is that the pulse waveform depends on the subject, and when the age increases, differences come out, for example, about the diastolic peak. It is strongly attenuated, and the diacrotic notch is almost disappeared. But also other information we can obtain. Because if we look at the second volunteer and on the entire recording, the sensor measured a sort of irregularity of the cardiac rhythm here, which corresponds to an arrhythmia, more specifically a supraventricular extrasystole. This result was also confirmed by clinical exam subsequently done. But this information about the cardiovascular status can be obtained not only from the pulse waveform that we saw also before, but also if we calculate the second derivative of the signal, which corresponds to the pulse wave acceleration signal. And here we can see the typical waveform for acceleration signal. It is made by 5 peaks. named from A to E, and these ratios depends on the age of the subject. So we can obtain information by looking at this peak. And this is what we did for the same volunteers. So before, we calculated the acceleration signals, and we can see the similarity with respect to the theoretical waveforms. And we calculated these ratios, for example, comparing these two subjects. The first one is 25 years old, the other one 66. And as expected from the literature, B to A increases, whereas the other ratios decrease with age. For the second configuration, so for the measurements on the wrist, we can see that something changes because we are changing the body part where we are performing the measurement. And more specifically, this tide wave appears. This corresponds to early pulse wave reflection during the systole phase. And so here we can see an example of the recorded signal. We can see that the waveform is close to the theoretical one. And this acquisition allows us to discuss about another key point for pulse wave monitoring, which is filtering and the post-processing of the signals, because it has a strong impact on the analysis that we want to do. We need to properly filter the signal to have the content specific for the pulse wave phenomenon. And here we can see some comparison by considering the second order Butterworth bandpass filter by changing the lower and the highest frequency. And then we compared also different ages for the subjects. And here again, we see how much the pulse waveform changes. For the wrist, again, the diastolic peak is very attenuated, and also the tide wave is no more visible. So to conclude, we can say that fiber Bragg gratings show great potential for biomedical applications. And if we embed the FBG in soft compounds, we can have, of course, we can have soft sensors, but also stretchable, wearable, and we can make them sensitive to force, to transversal force and pressure. And these are important features for physiological monitoring. We investigated the application of pulse wave monitoring, and the results demonstrated that the measurements give information about systole, diastole, cardiovascular age, and also numerical simulations were useful to select and optimize the geometrical features of the device. So our future steps will be probably to compare the results also with the results obtained by using commercial devices, and also to perform experiments on patients. And so I conclude the presentation. Thank you all for your attention.
Thank you very much. Time for one question. Is there any question? Well, it's very nice, your presentation, because we are working in things related with that research. So, well, I think that, well, it's a bit tricky to work with fiber optics and fiber gratings. So, did you make many different trials to finally find the silicon embedding structure? Did you try other ways to embed the FPG?
Yes, of course. We use thank you for the question, different materials. For example, we can change the materials, we can change the geometries, as we saw. The difficult part is maybe the positioning of the, not of the FPG inside the patch, but of the patch with respect to the body part, because if we move the sensor, something can change. The sensitivity strongly depends on the material, and the silicone is perfect. We can say perfect for this application, for sensing pressure. But it's not so tricky. Thank you.
Okay, thank you. Let's thank Elena.